Hello, class. So this is the second video on section 5.1. As I mentioned in the previous video, the goal here is to define integration instead of doing it with antiderivatives, which is a little bit, well, which is non-intuitive right now. In the previous section, we didn't know where those symbols came from in section 4.9. Instead, we're going to define it in terms of approximating area. And in this form, it's going to be clear where the notation comes from, and then we'll see how integrals relate to antiderivatives. Okay. So in the previous video, we saw that the first thing we needed to learn was how to divide an interval into n subintervals of equal length. Right? So we saw a formula for that. You subtract the endpoints of the interval and divide by n, right? How many subintervals you want. Okay. So we did that in the previous example. Now that we know how to do that, we can actually go ahead and start approximating area. So let's just jump right into an example. Right? So example 1. Using rectangles, approximate the area underneath the curve y equals x squared plus 2 on the interval -4 to 4 by dividing it into A, 2 subintervals, B, 4 intervals, and C, 8 intervals, each of equal length, okay? So we're trying to find the area under the curve y equals x squared and above the x-axis, right? So I included that above the x-axis because if you look at the picture, if we look at the area underneath this red curve, well, that's infinite, right? It goes down infinitely. So I instead bounded below by the x-axis. So let me write here, this is y equals x squared plus 2. Okay, so what area are we interested in calculating? Well, the area from -4 to 4, bounded underneath this curve and above the x-axis. So we're interested in this area here. Now, this is not an easy shape, right? If this were a triangle, right? If our shape of a graph were a triangle, we could use the formulas from geometry, right? The area of a triangle is 1/2 base times height. This is a parabola. How do we find an area like this? That's why instead of saying find the area, I'm saying approximate the area. Now, how are we going to approximate the area? Well, we're going to do it by using rectangles. Okay, so let's start with part A. We want to approximate the area, this area in green, by using 2 subintervals, dividing this interval -4 to 4 into 2 subintervals. Okay. So for A, using the formula from before, if we want 2 subintervals, and we want to find the length of each subinterval, we subtract the endpoint. So 4 minus -4 divided by 2. This is going to be 4 minus -4 is 8, divided by 2 is 4. This is going to be our change in x. Okay, so what are our subintervals? We'll start with the left endpoint, -4. Add 4, or add change in x. This is the first subinterval. Now add change in x again, and we're done, right? Because we get to the right endpoint. So those are the 2 subintervals. Now what are we going to do? We're going to approximate this area with rectangles. Okay. So remember that the area for rectangle is base times height. The base of each rectangle is always going to be the length of the subinterval. So it's always going to be change in x, which in this case is 4. Now the question is, what's going to be the height? So for the height, we have a couple options. I want the height to be determined by the function. In particular, what I'm going to do is I'm going to draw a rectangle on the left endpoint, right? So on each subinterval, I'm going to look at the left endpoint, and whatever function value I have there, that's going to be the height of my rectangle. So for example, for the first subinterval, the left endpoint is -4. Right? So I'm going to go to -4, look at the function value there, that's 20, and that's going to be the height of my rectangle. Oh, that's not 20, it's supposed to be 18. Yeah, because the function evaluated at -4 should be 18. So let me write 20 again here. It's going to be 18. Should go somewhere below, like that. And that's going to be my first, that's going to be my first rectangle. It's going to be this whole big thing here. Now, of course, that's a big overestimation of what the area is. right? Because we see that rectangle with where the height is given in purple, the length is given by the change in x, which is 4. We see that we only wanted the green area. Instead, we're also getting this extra area here. But that's fine. Right? That's part of the exercise. Now, for the other rectangle, again, I'm going to start on the left endpoint of the next subinterval. The next subinterval goes to 0 from 0 to 4. So I'm going to go to a left endpoint. That's going to give me the height. So what's the function value on the left endpoint? Well, that's 2. So this is going to be my height here at 2. Okay. Now, in this case, you see that in this subinterval, we're actually underestimating the area. All I'm getting is this part in purple. What I should be getting is also the part in green. Okay? So that's why this is an approximation. Right? And I made a conscious choice. I decided that the height of my rectangle is going to be determined by the left endpoint of my interval, right? Whatever the function value is there. So based on this, what's the approximate area? So I'm going to use some notation here. What should I use? Say we use, let's just call it area. Area sub 2 for saying that we use 2 subintervals. Okay. So what's area sub 2 going to be? Well, we had, for the first rectangle, we had a base of 4. Remember, the area is base times height. Base was 4 times height. The height was given by the left endpoint. Right? That's the function value evaluated at -4. Right? So it's -4 squared. 16 plus 2 is 18. So that's the area of this rectangle on the left, right? Bounded above by the orange, by the purple height. Okay. Plus the rectangle given in the second subinterval, it also has a base of 4 or length of 4. What's the height? Again, look at the left endpoint of this subinterval, which was 0. Evaluate the function there. Right? So 0 squared is 0 plus 2 is 2. And that's the other purple height you see there. So here, approximately, the area is, well, 4 times 8. So here I use approximately first, but here in the second, I'm going to use equality because 4 times 18 plus 4 times 2, I can actually calculate that exactly. So 4 times 18, that's 4 times 8 is 32. So that's 72 plus 8, which equals 80. So if you want to approximate the area under the curve, just using 2 subintervals of equal length and using rectangles, right, with the height given by the left endpoint of each subinterval, we get an approximate area of 80. Okay. Now, we're going to do the same, but instead we're going to do it with 4 subintervals. So what I'm going to do is I'm going to copy this picture here. And I think I can copy and move it to another page. Yep, there we go. Move it here to the side. Now for part B, what we're trying to do, well, we're trying to do now not 2 subintervals, but 4 subintervals. And so what's the change in x going to be in this case? Well, it's still subtract the endpoints. So 4 minus -4, now divided by 4, the number of subintervals. This is going to be 8 divided by 4, which equals 2. So length of each subinterval is going to be 2. So let me erase this here. I'm going to erase the heights that I drew in the previous part. And we're going to do the same thing. We're going to use rectangles to approximate, and the height of each rectangle is going to be given by the function value evaluated on the left endpoint. Okay. So actually, since we're going to do this one more time, let me just copy this picture again, so I don't have to do it next time. I'm going to put it on another slide and go back here. So what are our intervals now? Okay, so let's again, we just start on the left endpoint. Oh, I think I changed the color to change the color. There. Okay. So you start with the left endpoint, which is -4, and add 2 each time. So -4 plus 2 is -2. Add 2 again, takes you to 0. Add 2 again, that takes you to 2. Add 2 again, that takes you to 4. Okay. And then as before, so each of these is 2, right? The length of each rectangle, or the length is going to be 2, the change in x. And again, as before, this is going to be the base for the length of each rectangle. What's going to be changing is the height. Okay. So again, as I mentioned in the previous example, we again look at the left endpoint and use that as the height of the rectangle. Okay. So for the first subinterval, the left endpoint is -4. So again, we're going to be here at 18. That's going to be the height. Now for the second, and again, notice in this rectangle, we're overestimating the area of this subinterval, right? Because we only want the part in green. Again, we're also getting this part in purple, right? So we're getting both. So we're getting more area than we should. Okay, for the next one, the left endpoint of the next subinterval is -2. The function value evaluated there is 6. So it's going to be the height. And again, you can see by the picture, this is an overestimate of the area there. Now the next subinterval, the left endpoint is 0, right? That's going to be your height of 2, right? Evaluated the function there. And as a reminder, the function is y equals x squared plus 2, right? So we go to the left endpoint, evaluate the function there. That's going to be our height. Now again, as before, notice that in this case, we're underestimating the area. We're getting less than what we should. Okay. Finally, for the last subinterval, the left endpoint is 2. The function evaluated there should be 6. So it's going to be the height. And again, in this case, we're also getting less area than we want. Okay. So what's the approximation then? Well, let's do area sub 4. So we're doing 4 subintervals. Right? So let's calculate it. All of the intervals have length 2, each rectangle. So we have 2. The first height is the function evaluated at -4, the left endpoint. As we saw, that's 18, plus 2 for the length, that's always the same. The height is the function value evaluated at -2, which is the left endpoint of the next subinterval. -2 squared plus 2, that's 6, plus, again, 2 times. Now, the next subinterval, the left endpoint is 0. The function evaluated at 0 is 2, and plus the next subinterval, the left endpoint is 2. The function evaluated at 2 is 6. So 2 times 6. Okay. Now we can add all of this together. Oh, this is an approximation. So let's just say this is just approximate symbol here. This is going to equal what? So 36 plus 12 plus 4 plus 12. What do we get? So 36 plus 4 is 40. Plus 12 is 52, plus 12 is 64. So with 2 subintervals, our area approximation was 80. With 4 subintervals, the area approximation was 64. Now, if you look at the pictures, which one do you think is more accurate? Look at this approximation with 2 subintervals. Look at this approximation with 4 subintervals. Well, it definitely seems like they're both off, obviously, but it seems like the one that's closest to the actual area is the one with 4 subintervals, right? See how much discrepancy there is between the area in each rectangle here in the 2 subintervals? Compare it with the discrepancy here. There is still a discrepancy, but it's less. For example, if you look at this subinterval here and this subinterval here, it's not the exact area, but it's close, right? So this approximation should be better. Let's do it one last time. Now we're going to do it with 8 subintervals, right? That was part C. Use 8 subintervals. So again, what's the change in x? It's going to be subtract the endpoints. So 4 minus -4 divided by 8, that's a divided by 8, that's 1. So now the change in x here is going to be 1. So this is still y equals x squared plus 2. Let's go ahead and draw everything. So we have 1 subinterval, 2 subintervals, 3 subintervals, 4 subintervals, 5 subintervals, 6 subintervals, 7 subintervals, and 8 subintervals. And again, just once you have the change in x, you start with the left endpoint and that change in x each time. Now, as before, we're going to go ahead and use the left endpoint of the function as the height of the rectangle. So for the first one, the left endpoint is -4. We've done this a couple of times. This gives us 18 for the function value. Again, an overestimate, but not as bad as before. Right? Compare this first subinterval with this first subinterval here, and even with this one, and the area overestimation is still there, but it's not as big. Okay. Now the next endpoint is -3, left endpoint. Right? -3 squared is 9 plus 2, that's 11. So that's this function value here. And again, an overestimate, but not by a lot. Next function value is -2. Next endpoint, is -2. -2 squared plus 2 is 6. So we're here. Again, not too bad. Still an overestimate, not as bad as it could be. Finally, the next, not finally, but the next subinterval, the left endpoint is -1. -1 squared is 1 plus 2 is 3. So if you notice here, we still have an overestimate, but not by a lot. The next one, left subinterval endpoint is 0. 0 squared plus 2 is 2. So right here, not too shabby, right? Pretty close, some approximation. Next, we have 1. 1 squared plus 2 is 3. Right, so now we're underestimating, right? But it still seems to be more accurate than before. If you see the discrepancies between the area and the area of the rectangle seems to be less. Next left subinterval is 2. 2 squared plus 2 is 6. So we go up to 6. That's the height. Next left endpoint is 3. 3 squared plus 2, that's 11. So I have a height of 11. And there we go. So again, you can clearly see that to the left of the y-axis, we're overestimating, and to the right, we're underestimating. So this isn't going to be the exact area, but again, just by looking at the pictures, if you notice the discrepancy between the rectangles and the actual area we're trying to cover, here it seems that we're getting the closest to the actual area. Here, we're getting less close. Here, we're definitely pretty far away. Okay, so you see the pattern here. The more subintervals we use, the more accurate our approximation is going to be. Right. So let's see what we get here for the area approximation. So let's call it area sub 8 for 8 subintervals. What is this going to be? So each subinterval length, or each rectangle length, is 1. So 1 times anything is just itself. So I'm just going to write it for the first one. We have 1 times 18 for the first height, plus, now since 1 by itself times anything is just itself, and I'm not going to write 1 anymore, just the height. Right? The next height is at function value at -3, that's 11, plus the function value at -2, that's 6, plus the function value at 0, that's 2, plus the function value at, where am I at? Wait, so -4, -3, -2. Oh, sorry, I forgot -1. Yeah, so function value at -1, that's 3, okay, plus the function value at 0, that's 2, plus the function value at 1, that's 3, plus the function value at 2, that's 6, plus the function value at 3, and that's the last one, right? The last height is given by x equals 3, and that would be 11. So if we add all of this together, what do we get? We get 18 plus, so I'm just gonna add it in a different order that's easier to add. So 18 plus 2 is 20, plus 11 is 31, plus 6 is 37, plus 3 is 40, plus 3 is 43, plus 6 is 49, plus 11 is 60. Okay, let's see what we got. With two subintervals, we get an approximate area of 80. With four subintervals, we get an approximate area of 64. With 8 subintervals, we get an approximate area of 60. What is the actual area? Okay. Again, by looking at the pictures, it should be obvious that the most accurate one should be a sub 8 when we use 8 subintervals. Okay. The actual area, what is that going to be? So I can actually calculate it in my head here real quick. So give me a moment. And you'll be able to do this once we relate this to antiderivatives. What's 4 cubed? 4 times 16, 64, plus 8, plus minus 8. So I'm getting that the area is 128 divided by 3, which is approximately what? Or actually, I'm just going to write it exactly. It's just a decimal. So we put it in a calculator. So 128 divided by 3. So we get a more meaningful number. So 128 divided by 3. It's about so actually it's a repeating decimal. So I'm going to write it as approximately. It's approximately 42.67. So again, we knew it from the picture that the closest area approximation to the actual one would be the one with 8 subintervals, but here we can see it. 60 is the closest number to 42.67, which we got from 8 subintervals. Okay. So that's the idea. What's the point of this example? You can always approximate area underneath a curve and bounded below, in this case by the x-axis. It could be bounded by something else, doing rectangles. And the other key thing to remember is, if you notice, the more subintervals we did, the more accurate the area was. So that's the thing I want you to note here. Okay. So that's this example. We'll see how to do this more generally so that we don't actually have to draw a graph. For these ones, I thought it was very useful to draw graphs so we can see visually what's going on as we do these approximations. We can clearly see when are we overestimating area, where are we underestimating, and see that there is a discrepancy, right? This is just an approximation.